Once again, on this video we are going to learn about continuous uniform distributions. Okay, so before we start off on continuous uniform distributions, I want to look at this. I want to contrast that with all the other different distributions and variables you've learned so far, right? Okay, now you've learned about discrete random variables in S1. Okay, that's basically you're given a probability distribution. You just have discrete values, because let's say a problem like throwing a dice. Okay, so you can get values of 1, 2, 3, 4, 5 and 6, and the probability is always a sixth. Okay, so these are discrete values. You're getting the probabilities for discrete values. Okay, continuous random variables are like this. You have a probability density function that looks like this. Okay, and if I were to sketch it, it looks like this. The area of this graph should be equal to 1, okay, because all the probabilities added should be 1, just like this. Alright, but these are continuous values, any value between 3 and 5. Alright, but you can't get the probability of a specific value between 3 and 5. You can get a range of values, like between 3 and 4, the probability of that, or 4 and 5. Okay, so that's an example of the continuous random variable. Okay, you also learn about the normal distribution, okay, which looks like this. Alright, you learned that in S1. You know that the area of this is equal to 1, but you didn't learn the actual function like this. Okay, you don't need to know it, but I'll show you what it is. The function is actually this. Alright, now you don't need to remember that, but that's what you get when you draw that function. You only need to know the shape of the graph. Okay, but now we are going to look at continuous uniform distribution. Okay, so we'll just think about what that means. Okay, continuous meaning it ought to be like this or like this, because normal distribution also deals with continuous variables, and it's a uniform distribution. So uniform must be the same value, like this. Okay, so it can take a range of values. Okay, so it's continuous, plus it's got to be uniform. All right, so it's something like this. All right, okay. So if I said that was 5 and that was 3, that would be half. Okay, so that's an example of a continuous uniform distribution. The area of the whole graph is equal to 1, just like what you find here with a uniform distribution here as well. Sorry, not the uniform, with a continuous distribution. The PDF always should be equal to 1, so just like this, but this is a uniform distribution. Okay, right, where would you use this type of distributions? Okay, now let's say you were waiting for buses, and the bus comes on time, or it usually doesn't come on time, does it? Okay, so it could come 10 minutes late or 10 minutes early. Alright, so you could use a continuous uniform distribution to describe the time it arrives. Okay, so x, so it could be minus 10 or 10. Okay, and there's an equal chance of it arriving 10 minutes early, 10 minutes late, or any values in between. Okay, so that value on the y scale would be 1 over 20. Okay, if you wanted to, you could have described that as a normal distribution as well. Actually, it's more of a normal distribution case than a uniform distribution case, because you'd expect the bus to come at a certain time, and it probably, there's a good chance it only takes a few minutes early or late. Okay, and there's a very low chance of it getting really late or really early. Okay, so it's more like this, but you could also make that a continuous uniform distribution type of problem as well. Okay, now let's look at the notation that you use to describe a problem that is modeled using continuous uniform distribution. Okay, so you'd say variable x, okay, is modeled as a continuous uniform distribution. Okay, so you use the letter u, and then in brackets you put the highest value and the lowest value, alright, of that problem. Okay, so if it were in this case, it'll be 3, 5. So that tells you that this problem is modeled using continuous uniform distribution. Okay, so a question would be, what's the probability of x being greater than equal to 3 and smaller than 3.5? Okay, So you'll have to work out the equivalent area. So I'll just use this graph here. So this one here, this graph here. So it's 3 to 3.5. So I want the area between that and that. So it's half times, basically you're working out the area of the rectangle, times another half. Okay, because 3 to 3.5 is another half, which is 0.25. So that's the probability. So the answer to that is 0.25. Simple as that. Alright. Now, just like with the continuous random variables, for the continuous uniform distribution, you can figure out these parameters. Okay, you can figure out the expected value or the expectation value, the variance. You can also figure out the cumulative density function. Okay, because this is just a probability density function that you have here. This is a PDF. Okay, so you'll have to figure out the cumulative density function. Okay, so let's look at this, the expected value. It's very easy to figure out the expected value. Okay, because the distribution is uniform. Okay, the expected value would be always the middle value between the two values here, between the two limits here. So if it's 3 and 5, the expected value is this, 3 plus 5 divided by 2. The expected value is 4, because that's the value that's right in the middle. Okay, so if you look here, 4, I'll draw it with the red ink. Okay, 4 is right in the middle. Okay, expected value. Alright, that's simple. Alright, the other two are a bit more complicated. Alright, there is a standard result that you could use to work out the variance. Okay, there are two methods. So the first method is to use a standard result. Okay, that is this, that is b minus a whole thing squared divided by 12. Okay, now that b and that a stands for the two parameters that you have in your continuous uniform model. All right, so that's a and that's b. B is the highest value and a is the lowest value. So you do that to work out the variance. Okay, that's the easiest way to figure out the variance. Okay, sometimes they might ask you to integrate and figure out the variance. All right, what you would have to do is this. Okay, this is the same formula that you use to work out the variance of the continuous random variable. Okay, that's from chapter 3, the same formula that you used. Okay, this time your f of x is what? It's a half, isn't it? Because what's the equation of this straight line? It's half, isn't it? It's y is equal to half. Alright, so therefore if I plug that into this equation here, so that's half x squared. Well, this is done separately, I don't integrate this. That's basically my mean, my expectation value squared. Okay, my expectation value was 4, so that squared is 16, so I'll just keep that aside. Alright, and my limits here is 5 and 3, so I integrate it and find the result there. This is the result that I get when I integrate. Okay, so you could see that if I've done this, if I use the standard result, alright, I'd get the same answer. Okay, because that's 5 minus 3, which is 2 squared over 12. 2 squared over 12 is 4 by 12, which is also a third. So you get the same result. Okay, if they ask you to do this, then they'll say by integration show what the variance is. Okay, if they just say figure out the variance, you have all the liberty to use this, but if they say specifically in the question use integration to figure out the variance, you'll have to follow these steps. Okay, right, let's move on to the cumulative cumulative density function, or the CDF, of a continuous uniform distribution. So you're basically looking for a function basically that tells you the probability up to that value. Okay, the probability up to that value. All right, so I've got to now use sort of general values. So I'll call this b, I'll call this a, and what's this value here? It's 1 over b minus a, isn't it? That's always that value there on the y scale. All right, so I'll have to figure out a function that tells me, okay, the probability up to a certain value between a and b. Okay, so just like what we did in chapter 3 on S2 for the continuous random variables. Okay, to figure out the PDF. the CDF, the cumulative distribution function, we integrate. Okay, so my function here is 1 over b minus a, and I integrate it, all right, between, okay, a is the lowest value and any given point here. Okay, x could have a value anywhere here, isn't it? All right, so I integrate it. Okay, and I've done this here, all right, and I get this as my result. Okay, now basically what this means is this. Okay, so let me draw another uniform distribution. So if I call that 2, call that 6, this should be a quarter. All right, b minus a is at the bottom. Okay, so that's 4. All right, and x is there, and my a is 2. Okay, so the CDF, sorry, for this function is this. Okay, so I've got to put in the parameters where this applies. So x has to be greater than or equal to 2, greater than or smaller than or equal to 6, and for 0 it's 0, and anything above any values, I shouldn't have said 0, for any values smaller than 2, the probability is 0. For any values where x is greater than 6, it'll be 1. Okay, so that describes the probability density function. You got to write a capital F for that. The cumulative density function, sorry, CDF, is this. Okay, so you might be asked for the proof, which is this, or you could just choose to remember this to know how to work out the cumulative density function for a continuous uniform distribution. Okay, now I have a question here from the Excel book. Now let's try to answer this from what we've learned so far. Okay, a coffee machine dispenses coffee into cups. It is electronically controlled to cut off the flow of coffee randomly between 190 ml and 210 ml. The random variable x is the volume of coffee dispensed into a cup. Okay, specify a probability density function of x and sketch its graph. Okay, because the values could take any values between 190 and 210, it's totally random. Okay, you use continuous uniform variable to model this problem. All right, so your variable x is modeled as a continuous uniform variable. All right, and could have parameters where the values are between 190 to 210. Okay, so that's the first question solved. I also have to sketch it. All right, so the sketch would look something like this. So I just say 190 is here, just say 210 is here. I draw a little block there, and this value is 1 over b minus 8, so that's 1 over 20, which is the difference of this. All right, okay, so let's call that x and that's y. Right, okay, so part B, the answer is, let's say, okay, find the probability that the machine dispenses less than 198. Okay, so I'm looking for probability that the area of the block, which is from here, 198 is probably here to here. Okay, the area of that block, so that'll be 198 minus 190 times 1 over 20. So that's basically 8 times 20, 1 over 20, so which is basically, if I simplify that, that's 2 over 5. Okay, so that's a probability 0.4. all right, so that's the probability. Exactly 198 ml. Okay, this is a continuous distribution. With any continuous distribution, you can't get precise values. Okay, the probabilities of precise values. Okay, but may it be normal distribution or may it be continuous random variable. A distribution like this, you cannot get a probability for a discrete value. Okay, unless the distribution was like this, where it was a discrete random variable. All right, so the probability for that would be 0. Okay, because it's asking for a probability of a specific value. So part 2, the answer is 0. Okay, this is part 1. Third one, calculate the interquartile range of x. Okay, to calculate this, we need to know the CDF, the cumulative distribution function for this. All right, so let's work out the CDF. We'll use our standard result without bothering too much. Okay, so this is the standard result. So x minus a is the lowest value 190, and over the difference is 20. So that's a PDF for CDF for any values for x between 190 to 10. Okay, so I've got to use a capital F there for that, show the CDF. Okay, so I've got to figure out where if I want the interquartile range, I need to know the probability that, well, where the 25% probability will be at. Okay, so I'll have to equal this to 0.25 to know where the low quartile is. Okay, that would be the x. Okay, the low quartile would be at the 25th quarter probability level. Okay, or 0.25 probability level. So I've got to figure out what x is after substituting 0.25 for fx. I get my x to be 195. Okay, now I can see that that's my lower quartile. If I do the same, instead of 0.25 I put 0.75, I should get 205 for the upper quartile. Alright, and you all know how to work out the interquartile range, which is the difference between these two, which is 10. Okay, so the interquartile range is 10. Okay, I've just turned to the answers page on the book, and I checked these answers, and these answers are right. Okay, so I hope you found this helpful. I'll see you again on the next video. Bye bye.